Exciting to be back in the building together. 25 years, Brian. That's a big
it's
marker.
Scary,
it's an anniversary.
It's
so
scary.
I'm curious, are you a nostalgic person?
Very much so.
Are you very much so? You'd think I'd know this about you.
Yes.
So do you have these sort of like remembrances of being that guy, writing that book, hoping the reviews are good?
Yeah, well, it wasn't that guy. I don't think I ever got to be that guy. But I do remember, back in 1996, it was being in a little hotel room in Boulder, Colorado. I was leading a physics summer institute for graduate students, and I decided at that point pretty much to sit down to try to write the book. And it was unclear to me if anybody would have any interest, but I had this sort of overly romanticized notion that if the book inspired, one kid somewhere out there in the world to try to go into physics and answer some of these questions, it would be worth it, So that was the attitude I had.
Well, this is a good question for the audience. I'm wondering how many people read The Elegant Universe between 25 years ago and a few years ago. Yeah, I mean, that's a lot of people, and to have that kind of influence, it must feel strange to sort of see the life that it's had of its own.
Well, I mean, the real strange part is when you go places, a while ago, there'd be, a high school kid who would say, I read your book and I'm thinking about, maybe studying physics in college. You feel good, inspirational. Now it's, a professor comes along and said, I read your book, 25 years ago, and you begin to realize that,
Right.
over time it has a different impact.
Well, look, I know people ask you nebulous questions about time, so let me ask you one at this
Sure.
juncture. Do you imagine it's conceivable that there is Brian Greene of 25 years ago in some time location, in some sense, writing the book, and there's you in 25 years reflecting on the 50th edition? Do you think that time has a kind of persistent existence in the same way we kind of feel space does? Like, I think my apartment's still there.
Certainly in any classical perspective, yes, but you were quite optimistic to imagining me being around for the 50th anniversary, which I appreciate, but I think, I'm not quite sure about that. But yeah, I mean, what Einstein really taught us, at least in a classical universe, quantum mechanics were still struggling to understand what it says about time, but putting those subtleties to the side, Einstein really taught us that you and I, if we're in relative motion or experiencing different gravitational fields, we don't agree on what things happen right now. We don't agree on what it even means to talk about right now. My now could be your past. Your now could be my future. And so if you take into account all possible perspectives, real or hypothetical, of people moving around the cosmos, then sure, there is an observer out there for whom their now coincides, say, with me just sitting down in Boulder writing the first words of the book. And so if you give reality to those things that are happening right now, there's a person out there who says that event of me writing is right now. So in some sense, it's real and still there.
Now, I want everyone just to marinate on that. We start strong. We're going to come back around to how this whole conversation is changing around space and time. But I want to talk about this Washington Post op-ed that you wrote recently, just on Monday. Somebody's now. Somebody thinks it's just published. And you talk about a field electrified by string theory 40 years ago by a remarkable paper, and I think you mean a paper by Michael Greene and John Schwartz, no relation, different Greene. And I looked up the title to remind myself. It has the electrifying title, Anomaly Cancellations and Supersymmetric D=10 Gauge Theory and Superstring Theory. Do you feel like electrified? So I want you to help us understand, not just this paper, but where string theory was at the time, why it was so intriguing, and why this particular paper was a pivot.
So you're right. There were two individuals, Michael Greene and John Schwartz, who were sort of, toiling in obscurity at that time, excellent physicists, but they were so ambitious in what they wanted to accomplish, which was to put gravity and quantum mechanics together, something that nobody had previously achieved. And there was an approach called string theory that was already bubbling up a little bit, really since the late 60s. People had thrown around certain ideas, but there was a mathematical inconsistency in the formulation, and that is what kept most people from paying attention. And what happened in 1984, it actually was in Aspen, at the Aspen Physics Institute. Greene and Schwartz, they were at a blackboard doing some calculations, and they realized that in certain precise mathematical sense, this problem that had kept string theory in obscurity, they could get rid of it. And so they wrote this paper showing finally that this structure called string theory might make sense. It didn't suffer from this problem when understood in the right way. And when word of that reached people, physicists mostly around the world, the level of excitement was extraordinary. At that time, I was just beginning graduate school, right? You were in second grade or something. You know,
Thanks for that.
I was just starting graduate school at Oxford, and it's hard to put in words the level of excitement. People were saying, you know, here we are on the threshold of the final theory of physics. This is going to be it. The more mature people at the time knew that the road would be long even if this was the right direction to go. But the euphoria and the excitement, you couldn't help but getting swept up in it.
Now, help us understand in a few lines what string theory really is, why it's so successful, what it was about it that was so extraordinary.
Well, the answer to that question has changed over time, which I think is healthy. It shows that the field has been vibrant, it hasn't stagnated, it's not in a state of stasis. So perhaps the easiest answer is to give an answer that was relevant back then, and perhaps throughout our conversation there can be some updates to that as we go forward. But back then, we would describe string theory as a theory that rewrites the rules of the fundamental constituents. Everybody had learned, of course, in school that you take molecules, you get atoms, you get subatomic particles, protons, neutrons, electrons, you got quarks inside of the neutrons and protons. Those ingredients we envision as little tiny dots of no spatial extent, nothing further to be found within them. And the idea of string theory was to challenge that and say those little dots are actually little filaments of vibrating energy. And the different vibrational patterns produce the different kinds of particles. And miraculously, the move from a dot particle to a filament cures the mathematical inconsistencies between general relativity, Einstein's ideas of gravity, and those of quantum physics. And so suggests, a la this paper that you made reference to, that perhaps Einstein's dream of a unified theory was at hand.
Now, you can hear the unification in the very description. They're all the same fundamental loop and string. It's no longer this proliferation of different kinds of particles, all with these different descriptions. You're just looking for, as you said, different vibrational patterns. So there's something even in the simple description that gives you pause. Why is it so important that we have a quantum mechanical theory of gravity?
Well, you sound like my mom asking that question. No,
I planned.
Yeah. No. I mean, you know, my mother was always like, "Couldn't you have been a doctor?" You know, like, I am a doctor.
Well,
not
okay,
that kind of doctor. You know, this whole thing. But yeah, you know. So why would one care about these things? And interestingly, for the vast majority of questions in physics, you don't need a unified theory. Physics has done perfectly well just using Einstein's ideas when gravity matters, stars, galaxies, black holes, just using the quantum ideas when gravity doesn't matter for small things, particles, molecules, atoms, subatomic particles. But there are, in fact, realms that require both general relativity and quantum mechanics. If you think about the deep interior of a black hole, where matter has been crushed. A lot of matter, you need gravity. Crushed to a small size, you need quantum physics. If you think about the moment of the Big Bang, the entire observable universe, you imagine in some sense being crushed together, a lot of mass, small size, you need both theories. And so if you don't want to give up on deep questions, like what happens in a black hole, or how did the universe really begin, ultimately you have to grapple with putting general relativity and quantum mechanics together.
Let's talk about your mom for a second. So, your mom wants you to become a doctor. I don't know if that's even really true, but where in this experience of life, growing up in New York City, were you exposed to the concept of like theoretical physics? Were there theoretical physicists in your family who were hoping you would go in this direction?
No, my family was definitely not in the science arena. My dad liked to say he had an SPHD. Seward Park High School dropout. He was a musician. From the age of 14, he went on the road singing, playing harmonica, vaudeville acts. I mean, that was a completely different arena. But he certainly loved the ideas of science and mathematics, so certainly the love of it was there. But I do remember one very specific day. It was about 7th grade, walking to school, IS-44, public school in Manhattan, and having this sinking feeling of, the kinds of existential questions that any teenager grapples with, like, why am I here? What's it for? And the thing that really occurred to me that day was, there can't be an answer, because were there one, everybody would know it. And so maybe it's not about trying to gain insight into those deep why questions. Maybe the best we can do is answer the how questions. Not why is there a universe, but how is there a universe? Not why, is the universe the way it is, but how is it the way it is? And that really began to push me in the direction of physics. Now,
one of these kind of provocative insights that you talk about string theory ushering in. There were a number that you talk about, and you have a new preface and a new epilogue for this book. And this isn't a newer idea, but I wonder if you could help people grasp why we start to talk about extraspatial dimensions in this context, and it is related to that pivotal paper. And this is a little space-time origami.
Yeah, that's a nice little picture of what the extra dimensions of space conceivably would look like. So where does it come from? It's one of the most difficult concepts to explain why we're forced to it without relying on some kind of mathematical crutch. So if you don't mind, I will do that, but happy to go in other directions as well. When we look at the equations of string theory, and this is really what Greene and Schwartz did back in '84, and people have done variations on the theme ever since, there is an equation that basically says that the number of dimensions of space minus 10 times a really complicated expression must be equal to 0, or the theory doesn't work. Now, as everyone remembers, if two things multiply to 0, one of them has got to be 0. The complicated thing is, it's not 0. So it has to be that the d minus 10 part is 0, so d equals 10. The number of space-time dimensions is 10. I swear to you, that's really this is not a cartoon version. This is really what happens. And so you're forced by the mathematics to confront either giving up the theory or admitting the possibility that the dimensions of space that we see around us might not exhaust the dimensions that exist in reality. And then you try to make sense of that idea because you're pushed into it because of the equations.
Hence the anomaly cancellations and supersymmetric d equals 10. Gauge theory and superstring theory. What a title.
Yes.
I love it. It's seared in my brain now. So you become very excited, thrilled by the energy that's going around, both in England, of course. Michael Greene is from England, and here in the US, and you do your own work specifically also on these spaces and the origami of these spaces, and very surprising and profound results. I think that they're surprising is so interesting, that the spaces are more flexible than you had imagined.
Yeah, no, I was sort of in the right place at the right time, because even before string theory, people had bandied about the idea that there might be more than 3 dimensions of space that we all know about. So I was already enamored of the concept and wanted to work on it. And then when string theory came along and required it, it was sort of this
Delightful.
match that I couldn't look the other way on. And I'd already pretty much trained myself on the basic mathematics necessary to investigate shapes like the one that you see on the board. You know, in college, I was really interested in geometry and differential geometry and things of that nature. So I was well positioned, even as a young graduate student, to begin to analyze mathematically the possible shapes for the extra dimensions. And you're right, my dissertation was all about that, revealing some strange qualities of these shapes and trying to see whether there might be experimental consequences of these curled up shapes for the extra dimensions, which is our explanation for why we don't see them directly. And so, yeah, it opened a whole arena of investigation.
Now, you're very, therefore, invested in string theory, both personally, professionally, but you say very clearly in this WashPo piece that you are an advocate for truth, not string theory. And I think that's a very important lesson for people to understand. You're not proselytizing. This doesn't have to be right for you.
Yeah, I sort of find it uncomfortable when there's a shorthand, maybe because of the elegant universe, maybe because of being out there talking about these ideas, that I proselytize for them, that I am wedded to them being correct. I mean, nothing could be further from the truth, because while it would be exciting if these ideas were correct because they themselves are intrinsically interesting, a new way of thinking about the fundamental constituents, extra dimensions of space, the possibility that space can tear. I mean, there's all sorts of wonderful ideas that emerge from these studies that I do find intrinsically exciting. But no, the only thing that ultimately matters is that our generation continues the march toward a deeper understanding of reality. And so the point that I was making there, and thank you for bringing it up, is if there were anything that undercut our confidence that these are sensible ideas to study, I wouldn't work on them any further. And I'm quite certain, by knowing my colleagues, that they wouldn't either. It's ridiculous. And so the idea that we pursue this is predicated on what's happened over the last 25 years, which is enormous progress in the mathematical understanding of the theory, even though we've not reached the promised land of having experimental insight into these ideas. And so, yeah, I mean, I wish we had experiment one way or the other, but as yet we don't.
So, of the provocative insights that you describe that string theory can be cited as responsible for. One of them is a lot to do with black holes and understanding the fusion of black holes and Hawking's story and quantum mechanics. And so I wanted to start by asking you, why are black holes such an important terrain on which we try to understand these things? Why black holes? Why not something else?
Well, sort of as I mentioned before, they are one of the physical entities that, now we actually know for certain that they exist. We had a lot of circumstantial evidence, 25 years ago, but now with the Event Horizon Telescope and you actually see black holes, there's absolutely incontrovertible proof that they're actually out there. And so you need to understand them. And the beautiful thing about black holes is they are ready-made laboratories that force general relativity and quantum mechanics to confront each other. So if you can fully understand black holes, that really will require you fully understanding how these two pillars of 20th century physics talk to each other. And indeed, a lot of the progress over the past 25 years has been in understanding black holes, answering questions that people asked, Stephen Hawking struggled with and tried to gain insight into. Some of these questions are now really well understood in a way that nobody could have done without these techniques.
The one that comes to mind that is so persistent, Hawking kicked off in his inimical way, is the black hole information loss paradox. Do you want to try. I mean, if anyone can do it, you can do it, Brian.
You mean what the puzzle is?
Give us a concise description of the puzzle and why it was so haunting.
Yeah, I mean, the puzzle is pretty simple to wrap your mind around. You know, we think of black holes as places in the universe where when things fall in, they can't get out. And the question that was raised was, well, if something falls in, it carries information with it. That can be literal. You can throw your phone or your laptop in, and clearly there's information there. But any physical entity carries information. It has the intrinsic information of how its own internal molecules and atoms are arranged. There's information in there. So anything that falls into a black hole carries information. The question is it lost from the universe once it falls into the black hole? Hawking thought the answer was yes. You know, Hawking said something to the effect of, you know, information gets caught within the curved folds within a black hole and it's simply gone. The puzzle...
I mean, that would be okay in a way. Why would it be okay at first?
In principle, the puzzle arises when you then think quantum mechanically. Quantum mechanics does not allow information to be lost. If you lose information from the universe, then the quantum equations are unable to chug forward. They grind to a halt. And so this is a real problem. If the information is lost, you sort of have to reformulate quantum mechanics, but quantum mechanics does such a wonderful job that nobody wanted to reformulate it in a manner that would allow information loss. So the puzzle for a very long time was, what happens to the information carried by things that fall into a black hole? That was the puzzle.
And of course, Hawking also observed that because the black holes, in some sense, a tricky sense, where they're stealing energy from the empty space around them, are evaporating, eventually they expose this, it's a real crisis.
That makes it even worse.
Everything is exposed.
Yeah, absolutely right. So, I mean, Hawking himself, as you're pointing out, in 1974, showed us that black holes are not, as we often say, completely black. Quantum mechanically, some radiation can leak out from a black hole, and that radiation, when it goes off into space, carries energy. So the black hole gets smaller and smaller and smaller as its own mass is converted to energy that races away in that radiation. When the black hole squeezes down to nothing, now the information that fell in, it seems to truly be gone unless somehow it can come out. Hawking did not think initially that this radiation could carry out the information of what fell in. We, when I say that, I mean the royal we, the whole community of string theorists and more physicists generally speaking as well, now think that's not the case. We think the information does come out, and that really emerged from thinking of things in a string theoretic context.
I believe the way you phrased it was that any infalling particle leaves its essence imprinted on the event horizon.
And that can itself ultimately come out.
And that therefore can escape because it doesn't fall all the way into the black hole. So that's one of the very provocative results of string theory. It was able to get this towards some coherent description, and things have sort of heated up since then. But before we get into some of that, the really latest, most exciting, sort of thrilling results, you discuss 3 developments in your epilogue that make a continuous story from 25 years ago today. And one of them you begin with is laboratory experiments and astrophysical observations. So it's about 10 years after The Elegant Universe is published that the Large Hadron Collider powers on and eventually subsequently detects the Higgs particle, also known as the God particle. Somewhat disappointingly, and tell us in context why that was such an important development and how that relates to string theory, because it sounds to me like a particle again and not part of string theory. So how does that push us along?
Well, I wouldn't say that the discovery of the Higgs directly relates to string theory, and I wouldn't be so bold as to say it has anything to do with our assessment of string theory per se, but I would say that the pattern that it evidences is exactly the pattern that keeps us going. Because if you think historically, Higgs and others came up with the idea for this particle that would give mass to other particles way back in the 1960s. When the idea first came out, It got rejected from the journal. Nobody paid attention. Higgs stayed at it, began to convince people of the potential viability of this idea. It begins to catch on. People get excited about it. They work at it. By the time I was a graduate student in the 80s, there was almost a foregone conclusion that this idea was correct, so much so that I didn't even know at the time that it hadn't been experimentally confirmed. That's how certain people were, but it hadn't been. We build these accelerators, in particular the Large Hadron Collider, and then July 4th, 2012, the announcement comes that the particle is confirmed. So here you see this beautiful example, a mathematical idea that begins in the mind of Peter Higgs and some others. It wends its way through the community, is developed, is understood, is then finally tested, and the mathematics correctly predicts how the universe behaves. And so it's just a wonderful example of how mathematical ideas, for reasons that we still struggle to understand philosophically, but mathematical ideas somehow have this uncanny capacity to give us insight into how reality actually behaves. Will string theory go along the same pattern? We certainly hope so. And it's the success of other mathematical ideas, at least in part, that gives us some confidence that this is the right language and the right trajectory to follow.
So as you say, the discovery of the Higgs particle specifically isn't stringy, but it suggests that maybe string theory is not far behind exactly in this experimental campaign. What were the sorts of things that you might have hoped to have seen at the Large Hadron Collider that would have been that confirmation of this paradigm?
Well, we did anticipate, and part of the motivation for building the Large Hadron Collider was not just the Higgs, but it was also to find a collection of particles that are a natural implication of string theory, but, and this is the important but, which was I stressed in the book 25 years ago and stress every moment I talk about it since, we don't, from the math of string theory, know how massive, how energetic these new particles that string theory seems to require should be. And that creates the interesting possibility that if you build a new machine, maybe it will be sufficiently powerful to conjure these particles into existence through these incredibly energetic collisions between protons going around this 17-mile tunnel near the speed of light, opposite directions slamming into each other. Maybe that collision will produce these particles that string theory suggests should be there. We've been looking for those and we've not found them. And so what does that mean? Does it mean string theory is wrong? I wish it did. Again, if we could rule this theory out and put it to bed and turn our attention to other things, fantastic. All this does, though, is tell us that the particles might not exist, or if they do exist, they're at an energy scale beyond the reach of the Large Hadron Collider. And so we had hoped, certainly when I was a graduate student, I would have hoped that if I was having a conversation here in the year 2024, that it would be a known result. Either these so-called supersymmetric particles are out there or they're not, but we're in that limbo place.
Now, there must be some energy at which you would say, okay, we've gone high enough that we're certain we've scanned the entire conceivable range. And how much higher in power would you have to go than the Large Hadron Collider, the most powerful machine on Earth?
Unfortunately, you'd really have to go much, much higher to be able to make a statement of that sort. So much higher that it's inconceivable if you wanted to sit here and say, you know, what would it take to rule this theory out? How high would you have to go beyond the reach of any terrestrial, astrophysical, beyond the reach of our experimental capacities? And so, could it be that we find the particles at the next machine or the next machine? Certainly. But if we don't, we'll be in exactly the same situation as we are now, which, as you can see, this is why there is a small coterie of very vocal critics out there on the internet saying, you know, string theory's dead, you know, no experiment, you know, it's all nonsense from the standpoint of what I'm describing here, but I certainly get what they're saying. We wish that we could definitively say, look for this, it's in the capacity of that machine to find it. If you find it, it's information supporting our ideas, but if you don't find it, it rules it out. I wish we could do that. We can't.
So there are astrophysical engines that can often do what we can't do with our limited resources here on Earth. Things like black holes that can be incredibly powerful engines. Are there any astrophysical sources that are basically cosmic colliders that will hit this million billion times more powerful than the Large Hadron Collider?
We'd have to be so lucky, so fortunate that it's not something that I'd ever want to publicly say, that's the way that we're going to determine whether string theory is right or wrong, because again, the odds are we'll be in the same situation after searching for those astrophysical signatures, which is not to say that you shouldn't come up with creative ideas. I mean, you know, some of our colleagues here, we've kicked around ideas. There are things that you can write down in order to try to push the dialogue between string theory and experiment or observation forward. But nothing that you can write down will be definitive in the sense that if you don't find it, it rules the theory out.
The astrophysical observations that you describe were also very surprising over the past 25 years. In particular, that the universe is not just expanding, which Hubble observed and realized, but that the expansion's getting faster and faster, it's accelerating. That's a real surprise, and we give it this proxy name, dark energy. How does dark energy tie into this larger story?
Yeah,
there's astrophysics, large space, and then there's these small microphysics of the colliders.
Yeah, so you're absolutely right. It is a big surprise to learn that space is filled with this, we believe, diffuse energy. It's called dark energy. It doesn't give off light, which gives rise to a repulsive gravity that is pushing things apart, causing the expansion of space to speed up over time, the accelerated expansion. And so one question is, can string theory give insight into the existence or even maybe the actual amount of dark energy? And this is something that people have spent a lot of time thinking about, especially when you look at the amount of dark energy expressed in the appropriate units. It's an utterly bizarre number. It's a number that, you know, is a decimal point followed by about 120 zeros and then a 1 after it. That's the amount of dark energy in the correct units, the natural units. The fact that it's not zero is vital. We believe it's what's explaining the observed accelerated expansion, but that's not the kind of number that we're used to finding in physics. We're used to finding numbers like 1, square root of 2, pi, e, you know, numbers like that. We don't have these crazy numbers. So you ask yourself, is there any way that you could ever do a calculation and have this number pop out? And the approach that string theorists have largely come to is of a very different sort. It requires a kind of rethinking of the very nature of reality. And we can discuss it if that fits into your plan. But it's, again, something that makes people very uncomfortable to hear the place where explaining that observation has taken us.
Well, I think that leads us directly to the second development that you listed in your epilogue, and I'm going to phrase it the way you did, which I think is very evocative. You said, did God have any choice in making the universe?
Yeah, that's Einstein. I'm quoting Einstein there, but yes, right.
You still, chose that phrasing, which I thought was very interesting.
Yeah.
So I'm not going to totally let you off the hook on it.
Yeah, well, I'm very interested in the way ideas of God do wend their way in this through different minds and physicists and so forth, but that's a separate conversation perhaps that we could have.
Can we talk about that for a minute before we jump off of it? So but might as well, we're here.
Yeah.
I know that is Einstein's phrasing, and he was confused as for being a very religious man when really many people argued, in fact, that was just his elegant way of phrasing it. But do you believe that there is a God making choices in the making of the universe?
I don't know. But I can go a little bit further. Look, what's my view? My view, which I think many of our colleagues share in one way or another, is that it's astounding how this brain of ours, which evolved so that we could survive in the African savannah, get the next meal, somehow this brain got so good at detecting patterns in the external world and finding the language to encapsulate those patterns, namely the language of mathematics, that we've been able to go so far overboard that we've been able to find patterns that are irrelevant to survival, patterns in the astrophysical realm, patterns in the microphysical, the quantum realm. This is utterly astounding to me that we are able to do that, and deeply gratifying. Now, could it be that there is some grand designer that is behind all those patterns? Certainly could be possible. But I don't find that answer from a physics standpoint to be particularly interesting, because then you sort of stop at that point. What I find interesting is to continue to probe deeply into those patterns for the sake of understanding them intrinsically, to see how far our brains can go to unraveling it all. And that, to me, is really what the scientific enterprise is all about. But unlike some of our colleagues, I find the idea of something beyond the physical, the idea of something that our forebears found deeply compelling, to me, I find it extraordinarily interesting to think about and pursue that idea. I don't consider it something that should ultimately be wiped off the face of the earth, as some of our colleagues have explicitly said, because in the end, we're human beings struggling to grasp who we are, how we came to be here, and what can give our lives coherence and meaning. And for some people, relying upon the kind of poetic stories that our forebears wrote down is something that helps them gain a foothold in that project of trying to make meaning and find meaning. And if it works for an individual, more power to them in this world of ours. And so, to me, these are dual enterprises that seek ultimately to give us insight into the nature of ourselves and the nature of reality. And we should make use of all stories that we can write down to try to give us a sense of understanding.
You say something to the effect that it's important to understand the profound influence of human nature, even in the ostensibly objective realm of science.
Yeah.
And I believe that's what you're alluding to, which I think is a very organic and more complete and open approach to the pursuit, though I also like the humanist stance.
Yeah.
So back to the scientific sense in which this quote was used. Does God have a choice in making the universe? There is a scientific sense in which you're posing that question again.
Yeah, no, for sure. I mean, Einstein had hoped that the universe would be so singular, so rigid in its structure, that the laws that, say, he was writing down, or perhaps the laws that he envisioned one day supplanting the ones that he wrote down, would be uniquely determined. One set of laws, one single, unique, unified reality. And I think many of us in our heart of hearts share that dream. There's something quite compelling about it, because if you ask the question, why is there a universe? The answer that this approach would give, there had to be. It would be a logical impossibility to not have a universe, because the laws themselves are so rigid in their structure that they don't allow for the other possibility of there not being a realm called the universe. So that's this dream that Einstein had. String theory, and actually many developments in modern physics, not just string theory, have taken us pretty far from that vision. And in particular, string theory, we spoke about those extra dimensions. Well, we've learned that the extra dimensions can have many different shapes. When I was a graduate student, only 5 shapes were known, which is what motivated us back then to investigate them very closely to see if they might give experimental signatures that we could look for. But that was in the 80s. By the 90s, people had found other shapes for the extra dimensions. The number grew to like 10,000 was a number that people would kick around in the 90s. And to make a long story short, certainly by the early 2000s, that number had ballooned to like 10 to the 500 possible shapes, each giving rise to different experimental signatures. And so that is about as far as you can imagine going from a unique universe with rigid rules to a structure that allows for this enormous range of possibilities.
So now we're in the land of the multiverse.
This is a multiverse.
And when you were first thinking of all of these things in the 80s and the 90s, were you hopeful that it would be rigid? Was that really something that was important to you? Were you excited about that prospect?
Yeah, that would be rigid enough. Yeah, absolutely. I mean, we knew that there were like, 10,000, and look, that was more than the 5 when I was a graduate student, but, going from 5 to 10,000, you'd say, well, there are other graduates. Students need something to do. They could study them one by one. If they're 10,000, it's a doable chore, you'd think, to sort of analyze them one by one to see if any of them give rise to a universe that looks just like ours. That was sort of the goal. But when that number grows to a number that dwarfs the number of particles in the observable universe, you realize you're not ever going to study them one by one, and it changes your attitude. So was that a disappointment? In some sense, yes, because I was enamored with Einstein's vision of a unique universe, and this was taking us away. But to go back to your question about dark energy, Lenny Susskind and others have shown that, look, if you have an enormous number of universes, you're basically guaranteed that a number of them will have the dark energy that we've measured. And so that's one possible way in which you might explain what we have found. You point to the right member of the multiverse whose dark energy agrees with our observations. So you're guaranteed, if you will, to find a universe in the math that could agree with that quality. So in principle, this is an explanation that we didn't have before.
And you're pretty comfortable with the multiverse these days. I mean, as you said, they crop up now. It's not just string theory. It's
that's
just
important.
sort of, it's like the idea that there are other planets. It's just kind of how it is.
Yeah, no, we've certainly seen that kind of move repeatedly, right? There's a time people love to recount this history. It's all familiar. The Earth, center of the universe, dominant structure. Then we learn that we're one of many planets orbiting the sun. The sun, is that? No, there are many stars. There's 100 billion stars in the galaxy. Maybe the galaxy, certainly in the early 1900s, we thought that. No, now we realize that there are hundreds of billions of galaxies. So you can imagine, why wouldn't you go to the next step? The universe, well, yeah, there's one. No, now we think maybe there are many of those. So it's not an unfamiliar move in science to go from thinking that something is unique to some plurality. But I wouldn't say, per se, that I'm comfortable with the multiverse. What I would say is, I think it is a tool that we have in our mathematical toolbox, and when we're confronted with problems that we can't solve any other way, then there are times when we might use that tool to see if it offers insight that we can't get using any other approach.
Now, this idea of having a multiplicity of universes, there's also a multiplicity of descriptions we're starting to understand, even if in this one. and this is really the hard stuff. I want you to brace yourselves. This is the third development that you describe. I'll just call it dualities or holographic dualities. One of the most influential papers ever written, as you mentioned, the most highly cited paper ever in theoretical physics, by Juan Maldacena from the Institute for Advanced Study, another stunning name. Do you remember the name of the paper? It's like, I looked this up also. It's Large N Superconformal Field Theories and Supergravity. Is that the name of the title?
Very close.
Are you electrified? Can you walk us through why this paper became the most highly cited paper in all of theoretical physics, and the absolutely, and it really is glorious, stunning conclusion that precipitates from that?
Yeah, largely because, well, I think there are a number of answers, but let me give one quick one. String theory for a long, long time was viewed as a fundamentally new approach to physics. Again, as I mentioned, this idea of little vibrating filaments, this is an idea that hadn't had a home in previous theories, putting gravity and quantum mechanics together in a new way. So string theory was sort of viewed as the natural next step in the evolution of thinking in physics. What Juan's paper did was show us unexpectedly that string theory, if I can just be a little bit loose in my language, is actually equivalent to the approaches that people had been using previously. It goes by the name of quantum field theory. It's basically quantum mechanics of fields. That successful approach, which is behind the standard model of particle physics and the discovery of the Higgs particle, that highly lauded but older approach is actually equivalent to string theory. It's as if they're just two different languages describing the same physical reality. So all of a sudden, number one, we realized that string theory wasn't so different from things in the past, which was very exciting because quantum field theory is experimentally tested, right? So if quantum field theory is experimentally tested and string theory is equivalent to quantum field theory, all of a sudden you can talk about string theory and experiment in the same sentence without it being ludicrous. Mm-hmm. Moreover, what this so-called duality, these two different languages, a quantum field theory language and a string theory language provided, it gave us new tools for trying to address questions that either quantum field theory couldn't do on its own or string theory couldn't do on its own. The analogy I used in the Washington Post article, which is imperfect for sure, but you know that the famous optical illusion where you've got like sort of the young socialite and the elderly woman, and it flits back and forth between the two as you blink your eyes. This duality that Juan pointed out, when you blink your eyes, it looks like string theory, and you blink your eyes and it's back to quantum field theory. And so all of a sudden, you have different ways of analyzing the same thing, and only by using both in tandem do you get the deepest insight. So this really set off a whole new arena of exploration.
Why use the string theory description at all if I can revert back to the early 70s and the huge successes and all the Nobel Prizes and all of the understanding of the nature of matter with regular good old quantum field theory?
So there are only certain kinds of calculations in quantum field theory that we can actually carry out. Nature has been very kind to us in that the quantum field theory calculations necessary to understand all the data at an accelerator like the Large Hadron Collider, a lot of those can be carried out. Some of them are quite a challenge to carry out, but we can get enough insight to match our predictions with experiment, which is thrilling and why we believe that quantum field theory is the right approach for describing things there. But there are a whole host of other calculations that are beyond the reach of any technique that we have in our quantum field theory toolkit. Amazingly, when you take those calculations and blink your eyes and recast them as string theory calculations, you can do them using the string theory technology. And so this is what I mean by you need both to get the deepest possible insight.
Now, this has huge implications for black holes, which we'll get to in a second, but one of the consequences is that you can imagine a universe kind of in a box, or as you've drawn here, I've extrapolated from your book, I've taken from your book. Imagine a string model of a universe inside a sphere, and a higher dimensional space inside the sphere. It has strings, it has gravity, it has black holes, it has an information loss paradox, it has all of these things that are very hard to solve exactly. Even though string theory's made great advances, we can't really calculate exactly watching the information coming out of the black hole. And then Juan maps this to the quantum field theory description. Can you help complete that story?
Yeah, so it's a wonderful story. It's an ongoing story, but perhaps the way to answer your question that ties in with what we discussed earlier. Remember, we spoke about this information loss puzzle with black holes. You know, does the information get out of a black hole or is it lost? Well, it's a hard question to answer, but here's the beautiful thing. If you put a black hole in the innards of the diagram that you see there, which would be the string theoretic description that you can't fully grasp because the calculations are difficult to do. If you then blink your eyes and ask yourself, what does that black hole turn into in the quantum description? It turns into a very ordinary, basically called a hot field theory, a quantum field theory at a non-zero temperature that lives on the boundary, the sort of grayer lighter gray area that you see there. And that's something that we understand really well. And there's no information loss in that description. And if there's no information loss in that blink description, blink back, and you conclude there's no information loss of the black hole in the interior. So that's one example where you get insight into profound puzzles by just blinking your eye, flitting between the two distinct descriptions.
So what does it mean if I can map this entire New York City, this experience of sitting on the stage, this sense that we are interacting as material beings, we also experience gravity. What does it mean to say I can map it to a theory that has no gravity and in fact isn't even three-dimensional anymore?
Yeah, that's right. I mean, it's good to point out that if you, again, these ideas are only mathematically justified in certain very special cases, but let's talk more generally here just so we can get the gist of the ideas. This duality would say that the physics taking place in this volume here would be absolutely equivalent to physics taking place on a distant surface that surrounds us. And this is why it's often called holographic duality. A hologram, what is it? It's a thin piece of plastic. You illuminate it the correct way. It yields a realistic three-dimensional image. We would be the holographic projection of the comings and goings of physics taking place on that thin, distant, bounding surface. We would be the holographic projections. And so the beauty of the question you ask and that dictionary between the two is certain gravitational questions that we can't answer in this realm turn into non-gravitational questions in this dual description. So you can say, wait, so is there gravity or is there not gravity? The answer is, it depends on the description. And each description is absolutely precise and perfect and on target. They just describe the same physics in different languages. And so it begins to show you that the things that you latch onto as part of physical reality are in part determined by the language that you use and the historical progression that gets you to those ideas. You know, if there are beings, in some sense, who think primarily in the hologram version, gravity would not be part of the vocabulary. And if we were those, I mean, we are those beings, if we could somehow wrap our minds into that perspective, that's how we would. But our history is such that we use this three-dimensional gravitational description, but this suggests that it's not the only one.
And that is really a spectacular consequence to precipitate out of this, as you said, very human pursuit. And it does depend on who you're asking, how you're asking, and how you're able to understand it. Which helps us turn to a kind of philosophical question, which you raise. And you really kind of conclude on this philosophical question, which has to do with the limits of explanation. And in fact, you've alluded to it in this conversation, the limits of mathematics itself. Are we pattern recognizing species because of how we evolved on the savannah? And have we confused that capacity for pattern recognition and creating some kind of mathematical analogy with an external reality? Have we confused that with reality itself?
I think we have. But most of our colleagues, actually, I don't even know what your view is on this, don't agree with that. I just saw, Professor Parrick in the front row cross his arms, put his legs out. He's like, okay, here it comes, here it comes. My view when I was younger was math is out there and we discover it, and it's amazing that we can tap into these ideas and so forth. My view has shifted over the decades where I think mathematics is a language that we humans invent. We invent it because we have found over time that this language is really good at encapsulating the patterns of the external world, and that has propelled us to develop it yet further. And so all of these mathematical ideas that we develop, they exist in our heads. They're not out there. I don't think the universe has some fundamental mathematical architecture that drives it from moment to moment. I do think there's regularities and laws. I don't know how they're expressed. I don't know the form that they take. But that regularity does convince me that there's some kind of organization out there that is ticking along. But I don't think it's the equations that we humans happen to stumble upon and develop here on planet Earth. And so that, to me, some people, I've spoken about this, or I remember, and some mathematicians are like, oh my God, you can't say that. That's like, heretical. We are uncovering the mathematical truths that are, it's as if, you undercut the reason for being. No, I think it's quite the opposite. It's much more spectacular, I think, that we're not discovering this stuff. It's much more spectacular that this 3-pound gloppy gray thing inside of our heads is able to invent these mathematical. I think that's more thrilling than just going out there and finding it and bringing it back home. And so I don't think it undercuts the beauty and the wonder and the transcendent quality of these ideas at all. But yeah, I do think it's all inside of our heads.
We have talked about it one time, and you said, oh yeah, imagine an alien civilization comes down and they say, oh my God, you still do math? We used to do that.
Yeah, absolutely. And they would pat us on the head and say, yeah.
How quaint.
Yeah, how quaint. But then, if you were to push me further and say, well, what approach are they using, the aliens? It's hard for me to think of anything that wouldn't, in some sense, be isomorphic to mathematics or mathematics. And I think that's just a limitation of my brain, or maybe the limitation of the human brain, to figure out what would be the organizational schema for explaining a reality that is not mathematically based. But I at least allow for the possibility that there is something deeper out there that is not something that just comes out of somebody's head.
Wow. Okay. Now I'm just gonna
Malik
pause.
is looking at me like,
give me a
what?
minute, everybody. This is an almost impossible open-ended question, and so you can answer with something slightly proximate. But in the next 25 years, if not what's on the horizon, which is probably impossible to answer and maybe somewhat presumptuous, because what's so wonderful about what we've discussed are the surprises, these unexpected turns. So if not what's on the horizon, what would you hope for? What would really just be gratifying for you in the next 25 years?
I think the big question is, what is time? Is it, again, something that we invent and impose on reality to organize events in some coherent manner, allowing us to describe them mathematically and make predictions for what will happen next? Or is time intrinsically woven into some kind of fabric of reality, and it's just part and parcel of how the universe is put together? So I think that is one very concrete question, which we're already making progress on. I mean, we don't have time for it, but I'll just quickly mention there are results that at least suggest that we can imagine realms where space and time as we know them have not yet coalesced. If you have a ordinary piece of fabric, it's stitched out of, threads of the material, but it needs to be organized correctly to be a shirt. It could be that the fabric of space-time similarly has to be woven in the right way before it has the properties that we are familiar with. And there could be realms where it hasn't been so woven, so there is no space and time using the conventional language of science. More deeply, obviously, I think the question that Leibniz asked, why is there something rather than nothing? And of course, it isn't just, nothing of empty space. I mean, it's truly nothing. It's a very difficult concept to grasp, but can we gain insight into why there is anything at all? That, to me, would be the big prize.
Well, I think that's a very inspiring place for us to close and open it up to questions. Absolutely gorgeous thoughts and conversation. But before we open to questions, there's a mic over here. Please join me in thanking Brian for joining us.
And thank Janna. Thank you.
Here we go. Someone's coming.
Yeah, whatever. I'll start. Okay, with a tough one. So it's often described that we have these high-dimensional spaces, strings vibrate in them, they're constrained as to how they vibrate, and then particles pop out. What's the mechanism that just goes from string vibrations to a particle.
Yeah, I think the real way to think about it is that the particle itself is the string. It's not that the particle pops out of the string. It's just that this thing that in the past we thought of as structureless actually has some structure inside. And in fact, if you think about it a little bit further, the energy of that vibrating string, you could imagine via Einstein's E = mc squared, embodies the mass of the particle. So why does the particle have the mass that it does? Because the string that makes the particle is vibrating in the pattern that it does. And so that's the linkage between particle properties in the old language and string properties in the new language. They're one and the same, there's just a deeper explanation because there's a deeper structure.
Thank you. And so not just mass, though, but all of the quantum numbers come out of
That's right. All of the quantum numbers, the spin angular momentum, the electric charge, the weak nuclear charge, the strong nuclear, all of those qualities would be more exotic qualities of the vibration, because it wouldn't be E = mc squared providing the dictionary between them. But we do understand the dictionary. We understand how those familiar particle properties would be embraced by a vibrating filament.
Thank you.
Thank you so much for your question. Do we have another brave soul? Yes, thank you.
Very brave. I don't actually have a question, so I guess that's being brave in that sense. But when you were talking before about the kind of what sounds like a blasphemy to say to a physicist colleague that the mathematics that you're describing about the nature of reality might only be a creation of the human mind. And it made me think of a kind of philosophically, at least an ancient Indian philosopher named Vasubandhu talked about this millennia ago, which is that there are three natures of reality. There's the nature of the imaginary nature, which is what we construct with our minds. Then there's the interdependent nature of reality, by which everything is interconnected in ways that we can't possibly imagine. And then there's the ultimate reality itself, which is unattainable in terms of our human capacity. So I just think as an offering, philosophically, there's a way that you can imagine that the conversation that we're having, and in this way, in the way we're constructing the conditions of our lives and our biologic reality and so on, has allowed us to create a reality by which we can describe things and then use those descriptions and create science and create whatever it is that we are talking about. And whether they exist in the way that we would like to think things exist is a kind of one nature of reality.
No, it's a familiar conversation. Just 30 seconds. I don't know if my brother's here. Is he? Probably not. But anyway, you know, back in the '60s, when I was just growing up, my brother's a good deal older than I am. He went and joined Hare Krishna, and over the years, every time, we'd have many conversations, but anytime we found something in physics and I would excitedly tell him about it, he would be like, oh, Vedic text number 9. It's like it was always already there. So yes, many of the relevant ideas, both from a philosophical sense, as you were talking about, and even some of the science-sounding ideas of vibrations, oscillations, have themselves found a home in other traditions, and I think that's actually really exciting.
I see someone at the mic, please.
In the first half of the talk, you talked about how it's been difficult to experimentally verify string theory, and then I think midway through the talk, you guys talked about this well-cited paper that essentially said there was a duality between string theory and quantum field theory, and then you suggested that the former or the latter is something that has been experimentally verified. So if these two concepts or theories share a duality, and one has been experimentally verified, how come it's so difficult to experimentally verify the other one?
It does. And the challenge is, when we talk about quantum field theory, it sounds singular, but the reality is there are an infinite number of distinct quantum field theories. And one of those in particular has been shown to be a powerful description of physics as we know it. It's what we use to describe physics at the Large Hadron Collider and all sorts of other realms as well. The dictionary between string theory and quantum field theory is not one where every single quantum field theory we currently know how to describe it in string theory and vice versa. So if we were talking about the string theory counterpart of the standard model of particle physics, which we don't know how to discuss at all, if we did, then indeed that would have experimental verification through the duality. But the ones that were able, the quantum field theories that we're able to bring into dialogue with string theory, it's not ones that we've experimentally tested. So it's a framework issue as opposed to a detailed experimental vindication of one particular approach.
Thank you so much for your questions. Brian is going to do a book signing. I just want to say I feel so fortunate we've been able to share this space-time point, that we've known each other, that we've collaborated. Thank you so much for coming tonight.
Thank you.
Thank you, everyone.